In this lecture, we're going to be talking about oxygen nucleophiles and how they do nucleophilic addition reactions. Now, we're going to take two simple ketones. We're going to take 2-propanone and we're going to take formaldehyde. We're going to react it with water. Okay, and it's going to form these things called hydrates. Hydrates are when you have a diol in the same carbon, right? Hydrate. So you react a ketone or a carbonyl with water, you're going to get a hydrate. Now, the mechanism for this, I want to get into this in a little bit, not now. I want to make a point about the equilibrium and where it shifts, and then we get into the mechanism. We're actually going to see what's called acid catalyzed and base catalyzed hydration. But here, I want to make a point about the equilibrium. Now, what can we say about the relative carbonyls and their reactivity? Well, we know that due to hyperconjugation, these carbon groups are donating electron density to that middle carbon. So I'll put a little baby delta positive in relation to formaldehyde, which we'll see, which just has weak little hydrogen groups. Those aren't donating electron density like these carbon groups are right here. So what's going to happen is we're going to feel a lot more positive on that carbon. That renders formaldehyde a more reactive molecule, unlike, say, 2-propanone. Now, this is important when we talk about the equilibrium of these two, and I'm going to just erase the arrow. Well, if formaldehyde is a more reactive molecule, it's more sensitive to attack from water. So it's actually going to favor hydrate formation. And what you'll notice about 2-propanone and the corresponding hydrates equilibrium is that we almost entirely get ketone. We get very little hydrate. I mean, the equilibrium is like, this is almost 99.9% of the product mixture, where if we just took formaldehyde, this would be 99.9% of the product mixture. That's how different this is. Okay, so that's just an important note to make. The reactivity of that carbonyl can affect the equilibrium of hydrate formation. Now, this reaction is extremely slow. I mean, just awfully slow. So we can promote it by using an acid or a base catalyst. Now, let me erase this here, and we're just going to stick to our 2-propanone. And now this here, the equilibrium that will incur with this makes it so that the reaction goes faster, not at a more equilibrium state. Okay, so that's an important note here, but just to keep things simple, we're going to draw an arrow. Okay, I apologize. So we're going to react this with H2O, and I said acid or base catalyst. I'm going to use an acid first, so I'm actually going to draw our acid catalyst in red, H2SO4. I will get into the base catalyzed mechanism in a second, but here we're going to show this mechanism, an acid catalyzed hydration. Okay, so let's get right into it. The first step is to activate the carbonyl. Sure, there's a partial positive charge here, but it's not like amazing, right? Water is a pretty weak nucleophile, right? That's the species that's going to attack and attach itself when they get deprotonated, which we'll see. But that carbon is not as partially positive as it could be. We can do that, and that's where the acid really shines, right? To promote this weak nucleophile coming in for an attack, it's going to do the following reaction. So this is H2SO4, just drawn in a different light. Our ketone is going to pick up a hydrogen, and it's going to get protonated. Now you'll see that this has one effect, and one very great effect. Well, actually it has two, but one drastic effect is that we have a positive charge on our carbonyl. This makes oxygen pull even stronger, and there's going to be a vast partial positive charge building on that carbon. And what happens next is water is like, okay, you weren't as partially positive for me to attack, but now I can't resist. My marker fell. Okay, it can't resist it anymore. It's going to attack. That's exactly what happens. So we're going to see that our ketone now becomes OH, and then we have H2O. So notice that there. We don't even have to protonate the negative charge, right? If water attacked this molecule without being protonated, i.e. this here, well, the resulting structure would look something like this, right? A negative charge and a positive charge, right? What's going to happen right away is the carbonyl is just going to kick that little group out. We're going to go right back to the ketone. So, yes, the water can attack, but it's not going to lead to our product here. It's just going to get kicked right off the water molecule. So, that's an important note there. The final step is just deprotonation. Water will come in and deprotonate to give us our hydrate. So that's the acid catalyzed mechanism, right? We're going to protonate our carbonyl to activate it. We're then going to attack with water. We're going to get a semihydrate here. We have a water molecule attached, gets protonated, and then we get our hydrate. Okay, pretty simple there. I'm going to go ahead and erase this, so take any notes if you need. Okay, so now we have a ketone, and now let's say we throw in sodium hydroxide as our catalyst. Well, we'll get the same thing. It's just this time it's a lot different, okay? It's a lot faster too. So first step is sodium hydroxide will attack. And this is base catalyzed, so when you draw this mechanism, you have to make sure that you regenerate your base, right? It's not like the base is getting used up. It's not base promoted. It's base catalyzed is what we call it. So hydroxide will attack, kick up electrons. We're going to get a hydrate. And notice what we have here. We're actually going to go right to that right away. OH is an extremely awful leaving group. Like, it attacked and it does not want to go back. Oxygen is like, negative charge is fine, but you're not kicking me off without making me positive. So, terrible leaving group that is right there. So oxygen, unlike acid catalyzed, if water just attacked, it couldn't just kick it off, right? It can't do that. So what's going to happen here is it's just going to be stuck with a negative charge, and it doesn't like that. So it comes over to a molecule of water, and this is where it becomes base catalyzed. Is that negative charge is going to pick up. We're going to reform hydroxide. So this is base catalyzed. Notice the mechanism. OH attacks, gives oxygen that negative charge. It does not like that. It can't revert itself. So it gets protonated, reforming base and forming a hydrate. That's hydrate formation. Now we want to get into another topic in this lesson, which will be called acetal formation. Acetal formation actually has good equilibrium in it. It looks something like this. You react an alcohol, and you're going to react this alcohol with an acid. Alrighty, so when you react the alcohol with acid, what you're going to get is what's called an acetal. Okay? So notice, we went from a carbonyl to a diether. We call diethers on the same carbon acetals. So that's an acetal. Now, the general mechanism for this follows as such. First of all, we're going to use some acid, and I'll just draw it as, I'm a little lazy. Please, God, forgive me. I'm just going to draw H+. A proton in solution gets picked up by our carbonyl. This activates our carbonyl. Remember, we just talked about that. Our carbonyl is activated. Now what happens? Actually, I should go. I'm going to run out of room if I go that way. So what happens next is our alcohol molecule is going to come in, kick up electrons, and we're going to get what's called, and it's not fully a semi-acetal yet, but we're about to fool it. We call it a hemiacetal when there's only one of these groups. So if we just had that, that would be a hemiacetal. So notice we have a happy OH and we have an unhappy alcohol on there. So what can we do? Well, to make things happy, we can deprotonate. And in this case, we can use another equivalent of our alcohol. It's going to pick up the H, dump electrons, and what we'll notice is we have that hemiacetal. So I want to make a good point in saying hemiacetal here. OH on one side, ether on another side. So the next step here is to get rid of OH. So what does it do? Well, if you want something to leave, especially OH, you need to protonate it. So it's going to pick up another hydrogen ion from solution. I don't like that. I really don't like that. So we're going to go the other way. See that's a lot more logical there. And we're going to get a water leaving group, as you'll see. And we're going to get our alcohol here. So the next step is, okay, oxygen has a positive charge here. So what do you think is going to happen there? Well, if it has a positive charge, alcohol can come in and kick it off, right? Now, granted, this isn't an equilibrium, right? Water will come right back and say, no, alcohol, you have a positive charge. Let me back in there. But for the simplicity of following the mechanism, we're going to show it as kind of the story here, right? All these reactions happen in equilibrium. It goes forward a couple steps, maybe it falls back a couple steps, right? It's an equilibrium, but at the end, you're going to get your final product. Now, when you do that attack, you're going to get this here. You're going to get your protonated alcohol on there. You're almost there to the acetal. You need a molecule of your alcohol to come and deprotonate, right? So the alcohol comes in, steals a proton, dumps the electrons on the oxygen, takes it from positive to neutral. You have an acetal. So hemiacetal, and then we go all the way to an acetal. That's acetal formation. Now, I want to make one more point, and there's a lot to oxygen nucleophiles, but nitrogen won't be so bad. So now we have to talk about protecting groups. Now, protecting groups is, okay, you have two functional groups, and you want to do a reaction to one but not the other, and you might get a mix of products if you were to do the reaction without protecting said groups. Well, you can do something to, let's say for this you wanted to do, I don't know, you wanted to do lithium aluminum hydride reduction. Okay, so you first do the lithium aluminum hydride, then the acid, okay? So notice how lithium aluminum hydride could either attack the ester, right, and kick out the ester and make an OH, or it could kick out this carbonyl and make an alcohol. So it's really indecisive on which one it will do, and you might get a product mixture. If you were to just do this, you might get, assuming that you use, let's say you only wanted to do one. So you throw the lithium aluminum hydride in there in a stoichiometric amount just to do one. You'll probably get a product mixture that looks like this. Okay, you don't want a product mixture. That is always a headache in the lab. So how can we make this reaction only favor, and let's say I want to do that reaction only. I only want to make the ester go away. Well, good thing for you, acetal formation can serve as a protecting group. We just have to add a step 0 in this case of using this acetal here with H2SO4. Notice it's going to cause a formation of a cyclic acetal, right? The one OH is connected to another by 2 carbon bridge. So let's go through the mechanism here of how that works. And this will not attack. And give me a second here. This group will not attack the ester, which is really, really good. We need acid first. So acid comes in, takes a proton, and we get an activated carbonyl. The activated carbonyl gets attacked by our acetal. So let's just say it's this oxygen that attacks. Okay, so it attacks as such. And oh, this is gonna be a bloody awful to draw. So notice it's kind of like a little, what's slipping my mind. I was gonna think of something to say there. It's kind of like a little hanging piece off the edge or something of some body. But this oxygen has a positive charge it's hanging on. It's just gonna get simply deprotonated by a species, so I'll just say ROH, right? Molecule of this. It's going to take back a hydrogen, and we're going to get this kind of little hanging piece here, and we're gonna get our alcohol. Alcohol comes in and takes a proton in solution. I did it again. I went over the arrow. No, just like that. Ay caramba. Notice how our ester is just completely unfazed. Now, the ester could react with some of the molecules in here, but it's not going to be to a very good degree as compared to the carbonyl. So we have our water leaving group. Okay, it's ready to leave. It's like SpongeBob. I'm ready. Well, oh geez, I forgot the acetal. Oh heavens. It's ready to leave, so this group kind of just comes back and kicks out the group. Sorry, that was really weird, wasn't it? It's gonna come around town, I suppose. Kick out our water. We're gonna get minus water. Water leaves, and we're left with this here. And this is gonna look really funky, and you're gonna be like, oh, what the hell is this? Well, it's just chemistry. Okay, so notice, it makes a cyclic product here. That alcohol comes around and clicks itself in, and it kind of forms a ring, but kicks out the water, okay? And the last step here of the acetal formation is just simple deprotonation. So we'll take some species of base and deprotonate it. Okay, so we have our acetal here. Now we are available to do the lithium aluminum hydride H3O plus reaction. Hopefully you learned this. Basically, it just takes a hydrogen, clicks it in, and it's going to push up electrons on the carbonyl. Acid protonates it, and then we kick out this species here, and it's just a whole thing. But just know that this group gets kicked out. Oh. I get a primary alcohol as a consequence, okay? Now to get our ketone back, what we have to do is, notice how we did this in an unaqueous environment until we reach step 2. Now, H3O plus, you might want to use H2SO4 instead, but in an unaqueous environment, right? Solubilize your hydrogens in the alcohol. The reason is because if we now use H2O, water, it's going to hydrolyze that back into the ketone. Basically, it just goes in reverse of this, right? But in the presence of water, it will just kick that group right out and favor the equilibrium towards the ketone. And that's exactly what we get. And of course, this is under acidic environments too. We're gonna get that. So notice we went from getting a crappy product mix to a ketone and an alcohol with the correct product that we wanted. Hope you guys enjoyed. That was a long one. That's oxygen nucleophiles, and have a wonderful day.